In March 2001, VVS Laxman, who was an erstwhile batsman in Indian Test cricket team, played one of the greatest innings in the history of Test cricket. He scored 281 runs in the second innings, and India were following on. This is considered as one of the greatest Test innings ever played by a batsman. What is very interesting is that Laxman played this particular innings under extreme pressure. In a sense, he was in some kind of a confinement, because in that particular opposition side in Australia, there were some great bowlers, including Shane Warne, and the kind of constraints under which VVS Laxman played that innings is considered as one of the greatest innings in the history of Test cricket. Now, today's topic is to understand how things actually can emerge out of confinement. The example what I just gave was some kind of a realistic real life example where you put people under pressure or under some particular kind of artificial confinement, then you actually can have new behavior. Similarly, in physics, when you confine objects into a particular space or for a particular time, there can be some very interesting emergence which can come out of it. There can be emergent phenomena, which means that you end up having something which is otherwise not possible without that particular confinement. So let me give you a very fascinating example where one actually can confine some kind of a matter and you steer them and you can self-organize them into very interesting geometries. This is a very beautiful article which is written by many researchers who work on various different aspects of soft matter. This is a paper which is published in Soft Matter, where many authors have put together their heads and come up with some very fascinating phenomena. I'm going to use this particular article to give you some fascinating examples of how confinement can lead to some self-organization, and it can also lead to something called a spontaneous order. So steering self-organization through confinement, I'm using the paper which is published on Archive, which is freely available to everybody. By the way, all the references what I'm going to use is all given in the show notes in this particular video, so do check them. So what is important for us is to understand how this kind of emergence process can occur. So let me go to the PDF of this article. Okay, now what you're seeing here is a very beautiful illustration of how confinement can lead to self-organization. So the idea is that you start with some kind of units. It can be any unit of matter, all the way from atoms, molecules, colloids, or it can be even human beings or something like that. You take these units and you confine them into a particular kind of potential, which means that you confine them in space or in time, and you end up getting some kind of a self-organization in this process. What is more fascinating is there can be also sometimes some kind of a feedback. So there can be a feedback. Once you confine them, there can be organization within that confinement. Due to that particular interaction between the individual constituents, it can now feedback on the whole geometry, and it can lead to some spontaneous ordering and fascinating dynamics. Now, what is more interesting in this particular article is that they have also looked at this perspective not only from small objects. So here is a very beautiful illustration. They take the scale of the matter and the units of matter all the way from molecules, colloids, microorganisms, grains, insects, humans, planets, planetary systems. So you can see every kind of object in this particular observable universe are under some kind of a self-confinement. Those confinements can be external confinement, or it can be self-reinforced confinement. So you can take for that matter protoplanet formation, galaxies which are very, very large, they also are some kind of a confinement. Or for that matter, you take some kind of organization of human beings. For example, you go to a mela. In the mela, there are so many people who are constrained to a particular street. So that is also a self-organized kind of phenomena, and they too are confined as a function of space and in sometimes as a function of time. In my own lab, for example, what we are interested in is confining objects using laser beams. So you actually can shine laser and the laser can create a kind of a potential well. It is just like you take a tumbler and put a small marble in that particular tumbler, and the marble actually gets confined into the tumbler because it would not have enough energy to escape that particular tumbler. Similarly, using laser beams, you can create such kind of tumblers which can hold objects inside them. And the phenomena itself is very fascinating. Some other time I'm going to explain to you how we do that kind of an experiment, etc., etc. But for now, what is important for us is to appreciate the fact that in nature you can have these kind of confinements across various different scales. That is the most fascinating kind of phenomena what you come across. Now, one of the most intriguing kind of confinement is a biological cell. So you can see that in a biological cell there can be various different compartments where different kind of molecules can be confined as a function of space and a function of time. This has turned out to be one of the most fascinating principles in physics and biophysics for that matter, where you are able to confine things to a smaller and smaller extent and study in natural situation how confinement can lead to organization, how molecules can actually now organize, or small colloids can organize. By the way, colloids means they are all small objects which are now dipped into, let's say, a fluid, and they are free to move around. For example, if you consider a toothpaste, it is also some kind of a soft matter, and you take toothpaste and put it in water and make it dilute, it is a colloid. Milk is a colloid because there are small protein globules which are now mixed with the fluid in the milk, and these globules essentially are colloidal matter, and they constitute various different aspects of our real life for that matter. Now, this kind of confinement is so fascinating that various different people have been thinking about it. It is also very fascinating that you can take such kind of confinement and look at what happens in a dynamic situation. So I'm going to show you some very fascinating video which I captured roughly about 4 years ago. What you'll see in this particular video is some ants, and these ants actually are kind of confining this particular sweet, and they also dynamically move around. So what you'll see in a few seconds is that ants actually organize themselves spontaneously to take this whole object as a function of space and time. Let's look at the video, okay? So now what you saw was that ants actually spontaneously kind of rearrange themselves, and they could take this particular object and move them around. This is one of the very fascinating aspects of nature, where you can really look at ordering which comes out of it, just because of the fact that individual decisions are now made into a collective decision. And this is all happening because of something called as mutual interactions. And there is also some fascinating research which is going on nowadays, which is also called as active matter research, where the matter itself actually has some kind of activity. For example, if you take cells, living cells, and put them into a particular environment, because of the fact that they are living, they can not only interact with the environment, they can also interact with each other. And if you look at that whole soup of cells, they actually have some very, very fascinating phenomena. Now, there has been so many interesting viewpoints on this particular confinement. In general, physics itself actually is done under certain kind of confinement. Let's look at what Feynman has to say about it, where Feynman, as you know, was one of the great physicists in our world. And you will see that in this fascinating video where he actually talks about how confinement leads to some very fascinating process.
If I can face this right, you're an original thinker. I would like to ask you, how would you go about designing maybe a miniature, somewhat smaller than granite beauty, an anti-gravity machine?
Anti-gravity machine.
That you could use for...
No, I can't. I don't know how to make any anti-gravity machine.
You would think it was fun.
It doesn't make any difference. I still don't know how to do it. What the game I play is a very interesting one. It's imagination in a tight straitjacket, which is this, that it has to agree with the known laws of physics. I'm not going to assume that maybe the laws of physics have changed, then I can design something. But I try, supposing it's everything that we know is true as we think it is, as if we do. If we're wrong, of course, we can redesign something with the new laws later. But the game is to try to figure out, with what we know, what's possible. So it requires imagination to think of what's possible. And then it requires an analysis back, a checking to see whether it fits, it's allowed according to what is known. Okay? And in the case of an anti-gravity machine, I immediately give up because my understanding of the laws of gravity are such that I don't see any way, it doesn't make sense for anti-gravity. Okay?
And this is a very famous line of Feynman, imagination in a straitjacket. That is science. That is the creativity in science, because you actually have to obey well-known laws of physics and yet innovate within that particular boundaries. And that is the reason why creativity is something very fascinating, because you cannot arbitrarily do anything what you want, but you have to constrain things according to the allowed principles of the way nature works. And that's the reason why doing science is also very creative in that sense. So this kind of creativity under constraint is something which has been exhaustively discussed. For example, here is an article in Harvard Business Review where they talk about why constraints are good for innovation. It means that you actually can constrain people under certain kind of resource constraints, and you do see people innovate a lot of interesting things. There are many examples in the history of science. For that matter, if you look at some of the great innovators, including Tesla, including various people like Edison, and all of them actually were constrained to work in certain way because there was some particular requirement. Alexander Bell, who also innovated the telephones, etc. So a lot of interesting aspects are related to confinement, not only in terms of intellectual confinement, but also in terms of resource confinement. There are some fascinating processes. Even in the realm of education, for that matter, people actually have been looking at education as a particular process in which you end up getting creativity due to constraints. So there has been a lot of understanding from that particular viewpoint. So there is an article in 2022 where they talk about how constraints can lead to very interesting studies and also various different processes in looking at many different phenomena. So there is a lot for us to learn. Finally, there was another person in that cricket match which I started this particular video with, who also played outstanding innings. In fact, he was somebody who had not yet established his position in that particular Indian cricket team, and that was Rahul Dravid. Rahul Dravid is, of course, considered as one of the great one-down batsmen India has ever produced, and all of us know his great batting statistics, etc. But he also actually did very well in this particular match. In fact, he scored that great 180 runs, which is considered also as one of the very important supporting innings ever played in the history of cricket, because VVS Laxman and Rahul Dravid actually played one of the greatest partnerships in the history of cricket. And if you remember, they played out the whole day, and eventually India won the cricket match and went on to win that particular Border Gavaskar trophy for that particular year. So in life itself, if you are actually constrained, don't worry too much, because sometimes constraints can lead to positive things. It is all dependent on how you think about those constraints. When people throw lemons at you, make them into lemonades. Bye-bye.